Okay, so we're discussing about that discrete Fourier transform. So last class we talked about the discrete Fourier transform, frequency, resolution, and today we talk about the discrete Fourier transform as a linear transform view. So before that, I just recap some portion of that previous lecture and then continue to the discrete Fourier transform as a linear transform view. Okay. So what is Fourier transform? We have already said DFT is nothing but discrete Fourier transform. X of k is equal to n equal to 0 to n minus 1, x of n wn kn, where wn is equal to e to the power minus j 2 pi by n. Okay. Then what we discuss? We discuss about the properties, the different kind of things. What is the magnitude response? Because x of k is a complex number, so it has a magnitude and has a phase. So this is the magnitude, real square plus imaginary square, and that the phase is tan inverse imaginary by real. And we discuss about the frequency resolution. So we know that f the relationship between analog frequency and sampling frequency. The sampling frequency is given, n is given, then how the k is related to the analog frequency we have discussed. Okay. So let's say another things. Let's say example, that some of the example we are talking about in DFT. Let's say I have an xn, let's say x of n signal, I have a signal which is let's say 1, 2, 3. Now let's say I want to compute DFT of length 4, but signal is, this is the 0th sample, this is the 1, this is the 2. So I have a signal whose length n, let's say m, is equal to 3, but I want to compute DFT whose length n equal to 4. So if I say, when I say n k equal to 0 to n minus 1, x of k, x of k e to the power minus j 2 pi by n k, or x of n n k, x of k equal to divided by n, that summation sign, this part. So if I want to do that, but I do not have of x of 4, because I have x of 0 is equal to 1, x of 1 is equal to 2, x of 3 is x of 2 is equal to 3. But I do not have, here what will come? If n equal to 0 to 4, 0 to 4 minus 1, so x of n, this x of n will come x of 0, x of 1, x of 2, then x of 3, because this is 0 to 3, 4 minus 1 is equal to 3. So what is the value of x of 3? So that means I am assuming outside the length of the signal, signal is 0. So I can say x of 3 is equal to 0. So I padded a 0 here, or insert a 0 here, and then I said x of n, do the DFT of length 4 to compute x of k. So that is called 0 padding. Even I can say x of n equal to 1 to 3, I can compute DFT of n equal to 8. Then I have only 3 sample, but I am computing 8 point DFT. So another 5 sample will be 0. So that means 5 0 I will be padded in the length of the signal. So my x of n will be 1, 2, 3, 0, 0, 0, because length will be 1, 2, 3, 4, 5, 6, 7, 8. So all are 0. So if I add 0, is it change anything? Why I add 0? Is it change anything? So what do you mean by when I say n equal to 8? Or what is the difference between n equal to 4? So n equal to 4 means I am divided 2 pi frequency in 4 part. So it is 2, resolution is 2 pi by 4. But when I increase n, that means when it is n equal to 8, resolution is 2 pi by 8. So I am increasing the frequency resolution, but signal wise there is no change. Signal wise, so including the 0, once I inserted the 0, it doesn't change the signal, but it improves that frequency resolution. But the problem is that it also increases that computational complexity. As I said, that suppose I have an x of k, so x of k is equal to summation of n equal to 0 to n minus 1 signal multiply by e to the power minus j 2 pi by n into k. Now I said that computational complexity, this is a complex number. So a complex number is nothing but a cos plus or minus j sine. So I can say it is a minus jb. So if it is a minus jb, so I require for every k I require n number of complex multiplication. So for n number of k I require n cross n complex multiplication. So when I increase the n using 0 padding in the signal, I am increasing the computational complexity, but calculation wise there is no change. I get the frequency response of the same signal of xn, but with better frequency resolution. Can I make, suppose I have an x of n and I have an 1, 2, 3, let us say, or 4, fourth number of, let us say 4, 5, let us say xn 4 and 5. So I have a signal x of n is equal to 1, 2, 3, 4, 5. So I have a length, so m is equal to 5. So m equal to 0 to 4, m minus 1 is 4, 0, 1, 2, 3, 4. Now can I do m equal to 4 point DFT? Can it allowed? Is it the signal? Suppose I applied a x of n DFT with 4 point, I get x of k, then I apply IDFT with 4 point, can I get back x of n? No. I cannot get back x of n. Then I have to consider part by part. So 2 part I can do it. So that I will discuss during the long signal DFT calculation. So that is called STFT, short term Fourier transform, that we will discuss later on. So but if that m is greater than n, I cannot get back the signal x of n. Aliasing will be happen. So what is the requirement? My DFT must be equal, greater than or equal to length of the signal. If it is greater than, then I can assume that all those signal which is outside the m are 0, which is called 0 padding. Let us say do one example with 0 padding. Let us say I have a signal x of n is equal to, let us say 1, 2, 3, and I want to compute 4 point DFT, n equal to 4. Okay. So I know x of k is equal to, carefully look at this, n equal to 0 to n minus 1 x of n e to the power minus j 2 pi by n into nk. Now I said x of 0, so I have to pad 0 here. Fourth sample is 0. So x of 0 is equal to n equal to 0. So I put n equal to k equal to 0. So k equal to 0 means n equal to 0 to n minus 1 x of n e to the power 0, which is nothing but a n equal to 0 to 4 minus 1 x of n into 1 equal to x of 0 plus x of 1 plus x of 2 plus x of 3. So 0 is 1 plus 2 plus 3 plus 0 is equal to 6. And x of 0, k equal to 0. So frequency is equal to 0. So it is nothing but an average of the sample. Average value of the sample. That's why x of 0 is called the DC component. It is not the energy. If I said energy, then x square has to be happen. Because if it is negative, it will be cancelled. So average, mean value of the signal. I am not doing 1 by n is not there. So I can say sum. Sum of the samples is x of 0, which is frequency is equal to 0. That's why it is called DC value. Okay. Similarly, what is x of 1? X of 1, n equal to 0 to n minus 1 x of n e to the power minus j 2 pi by 4 into n into 1. So I can say n equal to 0 to capital N minus 1 or 4 minus 1 x of n e to the power minus j 2 pi by or pi by 2 into n. So e to the power minus j pi by 2 is nothing but a cos pi by 2 minus j sin pi by 2. Cos pi by 2 0 minus j sin pi by 2 1, so equal to minus j. So instead of that I can write down n equal to 0 to 3 x of n multiply by minus j to the power n. So I can say it is nothing but a n equal to 0 x of 0 minus j to the power 0 plus x of 1 minus j to the power 1 plus x of 2 minus j to the power 2 plus x of 3 minus j to the power 3. So if I say x0 is equal to 1 into minus j to the power 0 1 plus x1 is 2 minus j to the power 1 means minus j plus x2 is 3 minus j to the power minus j square. So j square nothing but a minus 1 plus x2 is done. So now x3 is 0. So 0 into minus j to the power 3 is equal to, so it will be 0. So it is 1 minus 2j plus minus 3. So I can say it is nothing but a minus 2 minus 2j. Similarly, I can calculate, let's say I taken another slides. Okay. So now x of 2, x of 1 I have calculated. So k equal to 2, n equal to 0 to 3 x of n e to the power minus j 2 pi by n into nk, k equal to 2. So I can say n equal to 0 to 3 x of n. So I already said that this part is nothing but a minus 2 minus j, so minus j to the power n into 2. So this is nothing but a, I can say x of 0 minus j to the power 0 plus x of 1 minus j to the power 2 plus x of 2 minus j to the power 4 plus x of 3 minus j to the power 6. So I can say this is nothing but a 1 into 1 again plus 1, 2, 3. So my x of n is 1, 2, 3 and 0. So 2 into minus j square. So minus j square means minus j whole square, that means minus 1. So I can say minus 1 plus x of 2 is equal to 3 minus j to the power 4. So it is nothing but a j to the power 4. J to the power 4 is minus 1 whole square equal to 1. So 3 into 1 plus 0. So I can say 1 minus 2 plus 3. So it is nothing but a 2. Now similarly, x of 3 is equal to n equal to 0 to 3 x of n minus j to the power n into 3, which is nothing but a x of 0 minus j to the power 0 plus x of 1 minus j to the power 3 plus x of 2 minus j to the power, I can say 3 into 2, 6 plus x of 3 minus j to the power 3 into 3, 9. So I can say this is 1 into 1 plus 2 into cube minus j, okay, j square into minus j, so it is minus j. So minus j whole square into minus j. So minus j whole square means minus j, so it is minus j. Minus 1 is a plus j, so it will be plus j. Plus x of 2, x of 2 is nothing but a 3, 3 into minus j whole cube, whole 6. So minus j cube means minus, this is plus j. So minus j is plus j, so plus j into plus j. So plus j into plus j minus 1 and plus 0. So I can say this is 1 plus 2j minus 3. So I can say it is minus 2 plus 2j. Similarly, I can calculate x of 3 is done, x of 4 also. X of 4 if you see n equal to 0 to 3, again x of n minus j to the power n into 4. So which is nothing but again x of 0 into minus j to the power 0 plus x of 1 into minus j to the power 4 plus x of 2 into minus j to the power 2 into 8 plus x of 3 into minus j to the power 3 into 4, 12. So this part is 0. So this part is 1 into 1 plus x1 is equal to 2 into minus j to the power 4. So j square minus, so the j square into j square. So it minus 1 into minus 1 plus 1. 1 plus x of 2 is 3 minus j to the power 8. So minus j to the power 8. Again j to the power, so it will be 1 only, okay, plus 0. So I can say it is 1 plus 2 plus 3, which is nothing but a 6. So I get a sequence x of k, which is nothing but a first value is how much? First value I have calculated is how much? X of 0 is equal to 6. So x of 0 is equal to 6. 1 is, x of 1 is minus 2 minus j. So x of 1 is minus 2 minus 2j. X of 2 is 2. X of 3 is minus 2 plus 2j, minus 2 plus 2j. X of 4 is 6. If you see, the all even components are real and all odd components are imaginary. Even signal and odd signal. Okay. So if I want to calculate mod of xk, so if I want to calculate mod of xk. Then I know first sample is only 6. So mod of xk is root over of real square plus imaginary square. So 6 square is nothing but a 6. Amplitude. Okay. Then root over of real square plus imaginary square. What is the value? 2 minus 2. So 2 square means 4 plus 4. So I can say it is 6 root over of 8. Then again I have a 2. Value is 2. X of 2 is 2. So I know the value is 2. X of 3 is nothing but a minus 2 plus 2. So 4 root over of 8. Again I have 6. So this is mod value. Okay. So now if I want to plot it, this axis is my k. K equal to 0, it is 6. K equal to 1, it is root 8. K equal to 2, it is 2. K equal to 3, it is root 8. And k equal to 3, k equal to 3. So k equal to 0, k equal to 1, k equal to 2, k equal to 3. And k equal to, so 0, 0, 1, 2, 3, 4. So if you see, the xk will be not 4, xk, k is varies from 0 to n minus 1. So it is 0 to 3. So if you see, the same component is repeat back. So I will not write this one. Understand? So now I will explain DFT symmetry later on in the properties of DFT. DFT has a symmetry. It has a symmetry property. You can see the 6 is coming back. So I can say it is a symmetry property. N by 2 symmetry. Okay. So that I will come later on when we will talk about the properties of DFT. So that way you can calculate the DFT and see what you are seeing. So here x of n, now suppose I calculate, now x of k is calculated. Now if I take the IDFT of x of k, I should get back the signal of x of n. So what is IDFT? So I know x of n is equal to 1 by n, k equal to 0 to n minus 1, x of k multiplied by e to the power plus j 2 pi by 4 into nk. Let us say whether it is coming back or not, I have to check. So what is the value of x of 0? What is the value of x of 0? Is equal to 6. X of 0 is 6. 6. So I said x of 0 is 6. Okay. Let us say, so x of 0, this capital X of 0 is equal to 6. So I said 0th sample is equal to 1 by n, 1 by 4, k equal to 0 to 3, x of k into e to the power 2j k n equal to 0, so e to the power 0. So I can say it is nothing but a 1 by 4 k equal to 0 to 3 x of k. So now you do that. So 1 by 4 x of 0 plus x of 1 plus x of 2 plus x of 3. Now what you know? My x k is nothing but a 6 minus 2 minus 2j. So I just write down my x k. So my x k is 6 minus 2 minus 2j. Then again I think 2, then again I have a minus 2 plus 2j, minus 2 plus 2j. That is my x of k. So what is x of 0? Signal 0, first sample 1 by 4, summation I have already written. So x of 0, 6, x of 1, minus 2 minus 2j, x of 2 plus 2 plus minus 2 plus 2j. So it is nothing but a 1 by 4, 6 minus 2 minus 2j plus 2 minus 2 plus 2j. So 2j cancel, minus 2 plus 2 cancel. So it is nothing but a 1 by 4 into 4 is equal to 1. So x of 0 is equal to 1. Which is my first sample? I have considered signal is 1, 2, 3 and 0. So 1, 2, 3 and 0. I consider my x0 is equal to 1. Now what is x of 1? Is nothing but a 1 by 4, n equal to k equal to 0 to 3, x of k into e to the power minus j 2 pi plus 2 pi by n, nk, n equal to 1, k will be there. So e to the power plus j 2 pi by 4. So it is nothing but a e to the power plus j pi by 2, which is nothing but a cos pi by 2 plus j sin pi by 2. So which is nothing but a 0 plus j is equal to j. So I can say 1 by 4 k equal to 0 to 3 x of k into j to the power k, n equal to 1, j to the power k. So I can say 1 by 4 x of 0 into 1 plus x of 1 into j to the power 1 into j plus x of 2 into j to the power j square plus x of 3 into j to the power q plus c 1 by 4 x of 0 6 into 1 plus x of 1 minus 2 minus 2j into j plus x of 2 is 2, j square is minus 1, okay, plus x of 3, x of capital X3 is minus 2 plus 2j into jq, jq means j square into j. So it is nothing but what is j square is minus 1, okay. So minus j. Now if you calculate 1 by 4, 6, j minus 2j minus 2j square, minus 2j square minus 1, so plus 2, minus 2. Here will be minus j, so minus plus 2j and minus j, minus 2j square minus 1 plus 2, I think so. If you see, this will cancel, plus 2 minus 2, this will be minus 2, 1 will be minus 2. So minus 2, this will be, no, this is 2 plus 2. So this is nothing but a 6 plus 2 plus 2 divided by 4, I think so. 1, 2 will be cancelled, or 1, 2 will be cancelled, 6 plus 2 will be there, 6 plus 2 by 4. So it is nothing but a 8 by 4 is equal to 2. So x of 1 is equal to 2. So I can get back the signal x of n is equal to 1, 2 and 3 if I do the inverse DFT. Now if I told you, suppose I have a signal x of n is equal to, do it yourself, 1, 2, 3, okay. So x of n, if I take DFT, I get x of k. Now if I take IDFT, then I get x of n, that we have proved. Now instead of that, suppose I have an x of n, I take the DFT, I get x of k. Again, if I take DFT, what should I get? Should I get x of n or what should I get? You do it. Do it by yourselves. You check. This is the signal. Take the n equal to 4 point DFT, calculate and see what is coming out. So I know DFT. So I know x of k. X of k is equal to, I have already done it, 6 minus 2 minus 6 minus 2 minus 2j. Second sample is 2. Third is minus 2 plus 2j. Minus 2 plus 2j. Okay, this is the 0th sample. Now, if I say instead of taking inverse DFT, I take the DFT again. So what I will get? I will get x of, let's say this is x prime n. So let's x dash n is equal to, so n equal, let's say k equal to 0 to, I am considering this is a signal. I am considering this is a signal and this is another signal. So let's see, this signal is transferring to DFT. So k equal to 0 to n minus 1 x of k e to the power minus j 2 pi by n into nk. So if I say what is the value of x dash 0, I know it is nothing but a k equal to 0 to 3 x of k into e to the power, so it is 0, 1. So it is nothing but a, I can say k equal to 0 to 3. So x of k, so it is x0 plus x1 plus x2 plus x3. Again, so I can say the this is nothing but a 6 plus minus 2 minus 2j plus 2 minus 2 plus 2j. So this is nothing but a 4. So I can say x prime 0 is equal to 4. Okay, then you calculate x prime 1, x prime 2 and see what happens. Okay, so now let's now you can calculate DFT by your own. Okay, so next lecture let's talk about that linear transform view of the discrete Fourier transform, because I have already covered this example part in this lecture. So next lecture I go for the linear transform view. Okay, thank you.